Hi guys, welcome to the video about theory of numbers on AMC-8. So this particular problem is taken from exam of 2016. It's a problem number 24. So the digits 1, 2, 3, 4, and 5 are each used once to write a 5-digit number PQRST. The 3-digit number PQR is divisible by 4. Okay, let's recall the divisibility rule by 4. It says that this number that consists of two last digits, QR, must be divisible by 4. So I use this triple point symbol to designate divisibility. Okay, QR is divisible by 4. Then it's the first condition. The 3-digit number QRS is divisible by 5. Okay, we know that the last digit S must be either 0 or 5. But 0 isn't among the digits we are allowed to use, so the only possibility for S is to be 5. Okay, then 3-digit number RST is divisible by 3. It's one of the most popular divisibility rules, based on my experience, of course. R, S, and T, the sum of the digits, must be divisible by 3. Okay, we're gonna use S equals 5. So I can't use it in QR, but I can use it here in our RST. So R plus 5 plus T is divisible by 3. So I have not so much number of digits, so we can just guess what is R and what is T. Okay, to be divisible by 3, it must be a number. R plus 5 plus T must be a number. 3 doesn't work, of course. 6 doesn't work because we have no digits like 0, 1, and 9 is the first possibility. So if I want R plus 5 plus T to be 9, R plus T must be 4. So there are two possibilities. R equals 1, T equals 3, or R equals 3 and T equals 1. Yep, so I want to remind you that we use only the digits 1 through 5. So if let's assume R equals 1 and T equals 3, I can check this option using the first condition. If R is equal to 1, then this number is odd. Yeah, because its last digit is 1, and odd number can't be divisible by 4, so we dismiss this option. If R equals 3, it's the same story, right? So the 2-digit number QR ends with an odd digit, so it can't be divisible by 4, so we dismiss this option as well. So it's not 9. It's not 9, so let's consider next possibility. Next multiple of 3 is 12. So R plus 5 plus T is 12. So R plus T must be 7. So using the digits 1, 2, 3, 4, because 5 is already busy, S is 5, I can see that there are two options, R equals 3 and T equals 4, but it doesn't work again, right? Because we have already considered R equals 3. It didn't work, so discarded. R equals 4. Oh, that looks promising, right? R equals 4 and T equals 3. Because if R equals 4, there is a possibility to be divisible by 4. Okay, R equals 4, T equals 3, S equals 5. To make this number divisible by 4, apparently Q must be, look at the digits available, 2. Yeah, because 24 is divisible by 4. So Q is equal to 2. So the only digit we didn't use is P, and it's 1. Yep, P is equal to 1, so it's A. Okay, so this problem was about divisibility rules. So we can move to the next problem. Okay, let me use the blue color. For any positive integer m, the notation m factorial denotes the product of the integers 1 through m. Okay, I hope you are already familiar with this concept. What is the largest integer n, for which 5 to the power of n is a factor of the sum 98 factorial plus 99 factorial plus 100 factorial? Okay, so when I look at the number like this, so the first thing that strikes my eyes is that I can factor out something. So 98 factorial can be factored out because 90n factorial, so it goes as a factor into 99 factorial. It goes as a factor into 100 factorial. So when I open the brackets, so it's 1 plus, so imagine there are 99 factors, 1, 2, 3, and so on up to 99, and you take out 98 of them. First 98 factors, so you have 99 as the only factor that is left over, plus 100 factorial. I factor out 98 factorial, so I have 99 times 100. Yep. So if you have any doubts about the factorization, you can easily open the brackets and make sure it's exactly what you started with. Okay, 98 factorial, good. So let's work with what we have inside the brackets. So 1 plus 99, it's 100. 100 plus 9900. So 1 copy like of 100 plus 99 copies of 100. So it means we have like 100 times 100, so it's 10,000, right? So again, this is 100, then you added 99 times 100, so it's 100 times 100, right? So okay, now we have to count fives, the number of fives that go into this number as factors. So I know 98 factorial is 1 times 2 times 3 times 4 times 5 times and so on, times 10 times 15 times 20. So I extract these numbers because I understand that they have fives as factors. So if you're not familiar with the advanced technique how to extract the number of factors of 5 in the factorials, so we can just count them manually. 5 has a factor of 5, 10 has a factor of 5, 15 has a factor of 5, 20, 25, 30, 35, 40, 45. It's a long way. 55, 60, 65, 70, 75, 80, 85, and 90, 95. Yep. So each of these numbers has at least one factor of 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on. There are 19 numbers. So it was better to count these numbers by dividing 98 by 5. So you know it's 19 and something, and then round it down. So it's 19 numbers with at least one factor of 5. But not all of them has exactly one factor of 5. For example, 25, it contains 2 factors of 5. 2 factors of 5. 50 also has 2 factors of 5. 75 has 2 factors of 5. So in order to count this additional, so let me let me highlight them like this. In order to count them quickly, I take 98 and divide by 25. So it's 3 point something, but if rounded down, it's 3. And you can easily see there are 3 such additional factors of 5. So then we sum these two numbers up. So 19 and 3, 22 copies of 5. 22 factors of 5 are in 98 factorial. But each zero here, each zero is 10 times 5, each zero is 5 times 2. So each zero represents like a couple of 2 and 5. So 1 copy of 5 in this 0, 1, 1, 1. So 4 additional factors of 5. 4 additional factors of 5. So 22 plus 4 is going to be 26. 26 factors of 5. So, yeah, so I want you to pay attention at this technique. It allows you to find the number of particular factors in factorials. So, right in the same way, you could find the number of 7s or number of 11s as factors that go into the factorization of 98 factorial. But it must be a prime number, of course. I mean 5, 7, 11. So this is a technique to find the number of times a prime factor goes into a factorization of factorial, some factorial. That's it. So we can move on to the next question. Okay, it's AMC-8 2018, problem 21. So the fact that the problems we consider are close to 25, it means these problems are pretty difficult in comparison with the other problems. Say it's way more difficult than the problems from the first to, I don't know, 15s or 17s. So how many positive 3-digit integers have a remainder of 2 when divided by 6, a remainder of 5 when divided by 9, and a remainder of 7 when divided by 11? So in order to write it in mathematical language, I have to recall a very basic principle that says the dividend is equal to divisor times quotient plus remainder. So there is one requirement for the remainder. It must be bigger than or equal to 0, but less than the quotient. It must be strictly less than the quotient. So I think it's one of the most basic concepts in arithmetics. So the 3-digit integer we are considering, let's make a designation. There n. It's dividend, because I'm going to divide this number n by what? By 6, and we will have a remainder of 2. So n is a dividend. Divisor, I divide by 6. Quotient is the result of division, and I don't know the result. So I can say it's, let's say Q1, okay? Plus I add the remainder, it's 2. Of course, the remainder is strictly less than the divisor, and it's the case, 2 is less than 6. But I can write the same number, n, in a different way, with the remainder of 5 when divided by 9. So 9 is a divisor. It must be a new quotient. Let's call it Q2 plus remainder of 5. Then the same number n will have a remainder of 7 when divided by 11. It must be a new quotient, because every time I divide by different numbers, so that's why quotients must be also different numbers. Okay, so here you must notice a wonderful fact, because if you do not notice this fact, you are in trouble. The fact you have to notice is that the difference between remainders and the divisors, they are the same for all three equations. So that's why I add 4 to the both sides of the equations. So n plus 4 is equal to 6q1 plus 6. N plus 4 is equal to 9q2 plus 9. And n plus 4 is equal to 11q3 plus 11. Yep. So n plus 4 in the first equation is equal to this number, and it's obvious this number is a multiple of 6. So n plus 4 is divisible by 6. Likewise, n plus 4 is divisible by 9. I clearly see that from the number. It's equal to 9q2 plus 9. Of course, it's divisible by 9. And then n plus 4 is divisible by 11, of course. So now it's a famous property of divisibilities. So this numbers 6, 9, and 11, they have an LCM, 6, 9, and 11. The LCM is, what is LCM? It's 2 times 3 times 3 times 11, right? It's, what is it? This is 9, 9 times 2, 18, 18 times 11 is 198, 198. So it means that if n plus 4 is divisible by 6 and then divisible by 9 and then divisible by 11, it means that n plus 4 is also divisible by LCM of these numbers. It's divisible by 198. In other words, n plus 4 is 198 times, let's say, k. K is an integer. Then the numbers we are interested in, so they all have this form. 198k minus 4, where k are integers. So we must take into account n is 3-digit integers. So k must be probably 1, 2, 3, 4, maybe 5 also works. Yeah, but 6 doesn't work. 0 also do not work. It doesn't work. So here are the values of k that we can put here in order to produce 3-digit numbers, because n is a 3-digit number. I don't want to calculate the number n for each particular case, because we're asked about the amount of such numbers. So I understand that it must be 5 such numbers. So you put k to this formula and you get that numbers. So the answer is 5. Of course, you can reason shorter in the solution of the problems like that, but I wanted to show you the idea. And the idea was that the difference between the remainder and the divisor is always the same. It's 4. So it leads us to this property of n plus 4. It's divisible by 6, 9, and 11. So it also means it's divisible by their LCM. So then you can write down the general formula for n, and then you put gradually put numbers for k that produce 3-digit numbers for n. That's it. So the answer is E. So I hope you liked the ideas we met today. Good luck for everybody, and see you on the next video.